First, let us discuss the principle of virtual work. Okay, so we will consider a system and then we will make an instantaneous change in our position vectors Ri. Okay, this Ri's are our position vector. So here we say this infinite instantaneous change in our position vectors Ri is called virtual displacement. That is, the position vectors have changed, Ri changed, but our time t has not changed. Now for infinitesimal virtual displacement, we will denote it by delta Ri. Okay. So how will this delta Ri look? Delta Ri will look something as follows, right? Delta Ri will be function of what? Q1, Q2, dot 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 Qn. Here we have this n generalized coordinates. Okay. Now in case of equilibrium, what do we know? Force equals to 0, right? F of I equals to 0. What is I? This n particles that we had, this Q of I, this is the same index, F of I. I also runs from 1, 2, dot 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 n. Okay, capital N. And this is small n. Therefore, what will be our virtual work? dwi. It will be F of I dot dri. Remember, this is only for equilibrium, right? Equilibrium. F of I equals to 0 will not hold true when it is not an equilibrium case. Now for equilibrium case, what we can write? dwi equals to 0. Okay. Therefore, we can say this virtual work dwi equals to 0. From how did we conclude that? See, let us go back to the beginning. Instantaneous change in position vector is called virtual displacement. Now for infinitesimal virtual displacement, we denote it by delta Ri. Now corresponding to this delta Ri, that is infinitesimal virtual displacement, in equilibrium case, the work is 0. This work is known as virtual work. So what is the principle of virtual work? It basically states that the work done is 0 in the case of an arbitrary virtual displacement of a system from position of equilibrium. Okay, so the work done is 0 in the case of an arbitrary virtual displacement. What is our arbitrary virtual displacement? Is delta Ri of a system from position of equilibrium. Why equilibrium? We said in case of equilibrium, F of I equals to 0. I hope you understand this definition clearly. If not so, let me know in the comment section. I will try to elaborate it further. Okay. So this total force, let us say F of I, that we saw in case of equilibrium. Let us assume it is constituted of two type of forces. One is external force and one is force of constraint. Okay, this is external force or applied force. This is force of constraint, and this is net force, right? So now we can write this equation as follows: summation over n. As there are n particles, we said this runs from 1 to n. Okay, So it will be summation over n, or rather I equals to 1 to n, sorry. It will be summation over I runs from 1 to n. F of I a, this f we will replace it. Okay, this f of I will be replaced by this. F of I a plus f of I dot dri equals to 0. Now, see, this can also be written like this, okay. I equals to 1 to n f of I a dot dri plus I runs from 1 to n f of I dot dri equals to 0. Now what is this? Work done due to constraints. And what is this? Work done due to external or applied force, right? So in our system, first let us concentrate on system where this work done due to constraint is 0. So what we can write? That the virtual work due to applied forces is 0 if work done due to force of constraint is 0. What does this mean? If we consider this force of constraint, that virtual work due to force of constraint is 0, then work done due to applied, that is virtual work done due to applied force, will also be 0. That is I runs from 1 to n f of a I dot dri equals to 0. So now we will do certain sums using this formula. What does this basically say? For a equilibrium system, for a system in equilibrium, the virtual work for applied forces is 0, right? If we consider systems where the virtual work due to force of constraint is 0, in that case, this will also be 0, right? From here, we will later derive D'Alembert's principle. But first, we will do some certain sums using this. Okay.